Hello and welcome. In this video, we're going to review how you can compare battery life cycle performance across multiple test conditions and multiple batteries. This is a play off of the last video where we looked at coulomb counting, how you can programmatically assess the battery's usable capacity, both charge and discharge, based off of integrating the current that's passed through a battery over a period of time. So we're going to use the same data set that we covered in that last lecture. And if you're not familiar with coulomb counting, you might want to check out that video first. Now, for a quick recap, the data set that we're using is an accelerated aging test study that was conducted by NASA, the Space Administration for the United States. In that study, they tested 33 different battery cells. Each of them went through a different series of cycling and impedance tests. So they modified the current under the discharge condition, they modified the ambient temperature using different thermal chambers, and playing around with some of those factors. Once the cells lost about 30% of their usable capacity, the test was ended and the cells were deemed at their end of life. For more background on the test results, go ahead and check out the link below. Also, if you want to pull the data set, you can go directly to Kaggle and look for the NASA battery data set. With that, should be enough of a background. Let's dive into the data set. We're going to start with some simple code to calculate the capacity for a single cell off of one data file, and then we're going to extend that across life. Once we have that for a single battery, we're then going to use it and apply that same condition and loop through it for each unique cell or battery in the test data set. With that, let's begin with the code. So I'm going to start by importing some of our necessary packages. So we've got pandas for reading the data frame, or reading the data and setting our data frame, NumPy for doing some of our mathematical operations, and a plotting package using matplotlib. I'll also note that we're importing CSV, and that's because this will be very useful for efficiently reading and just looking at headers to make sure we have some good data quality coming in during aggregation. Now, there are some other packages we'll import at the very end, but this should be it to start. So if you downloaded the data set off of Kaggle, go ahead and put it in a directory and specify that path. We're going to read the metadata file that was provided. And let's go ahead and look at the tag. 9 might be a little bit much for our first row, so let's go ahead and just look at the first 5 data sets. Okay? So when we look at the data that's loaded, we should see that we've got, it looks like a couple different test types. We've got charge, discharge, and impedance. So files seem to be based off of what type of test is being applied. If they're doing a current discharge of the battery, a charge, or an impedance test. It's also useful that they have the test time, ambient temperature, and battery ID for each battery. Now, one thing of note is that they do have the capacity, but that looks like it's empty for some of the tests, right? So notably, we have it for each discharge, which would be your usable battery capacity, but we don't have it for charge. So we're going to go ahead and fix that. And to snag the capacity for each cell across the test files, we need to confirm that the headers are consistent for each of our battery ID, or for each file for each battery ID. So this might seem obvious, but in fact, if we're using different test equipment or channel setups, it's possible that the header information is not consistent for each of those files. So we're going to check this first by loading our metadata file. We'll extract the file names using our metadata data frame, and then we're going to use those names to extract the headers. So I'm going to do this by creating a list of our file names. Then, once we have that, we're going to strip out the ones that we don't want of our metadata. So, we're going to look at charge and discharge. And I'm going to do that using list comprehension. And next, we'll set the file path for each file that we're then going to read off of. After we've done that, I'm going to set a simple function to check the file headers. So we've defined here this getHeader function where we have the file name as an input, so a string file name that's provided. And then for each one that is provided in this function, we're going to open it, and we're going to just look at the header information. And we're going to return that. So this is going to be used to get our headers. This is going to be quite handy because we've got over 7,000 files, and so it would be pretty cumbersome to just use pandas to read each one as a data frame. It's going to take a lot more time to iterate through and run this operation. So with that, let's go ahead and run this. And it might take a couple seconds, so I'll go ahead and pause the video and then we'll resume. Oh, but it actually finished. Great. So you see how quick that is versus running through a pandas read operation to read through 7,000 CSV files. We got this in a matter of 1 to 2 seconds. So when we look at that, we've got this list of lists, right, of string elements where we have our voltage, current, temperature, current, voltage and time for our charge and discharge. Now, this doesn't seem to be super helpful to look at intuitively, right? And so what we'll want to do is then try to just make sense of the data. And what we can do to make sure that the headers are all consistent is we'll load this list of column headers into a data frame itself. And then we're going to drop the duplicates, and ideally there should only be one row. So if all the column names were consistent across each data file, we'll just see one row. And let's go ahead and run this. So I'm loading it in the pandas data frame and putting in this drop duplicate command. And then we're just specifying generic column names for the 6 columns that we'll read. Now, mind you, this is assuming that there's only 6 columns. If there were more than 6, this would strike an error. If there were less, the same thing. But nonetheless, let's go ahead and run the code. Okay, so what we see here immediately should be apparent is there are 3 different sets of column headers. So it's important that we checked. And it looks like those differences that we see are based off of our impedance test, our charge, and our discharge. So those 3 different test conditions have 3 different column header names. You notice that because if you look at the first and the last row in this data frame, you'll see that there's voltage load in column 5 and voltage charge. So looking based off of that, you can tell that one of them is probably the charge data set, the other is the discharge. And we know the middle one is impedance based on the rectified impedance column and the battery impedance value. So with that, we want to look at the capacity across time. And one simple thing we're going to do here is just make the assumption that we're not interested in the impedance impact in battery cell aging. So if we assume that impedance was performed in the same manner, same process across all the cells, let's just exclude that and then look at the difference by doing cycle charging and discharging across new temperatures, new current profiles. And the way that we're going to do that is I'm going to first create a list of cell IDs. So I'm going to grab that unique set of each battery cell ID, and then for each one I'm going to create a list of temperatures and that we're operated with, and then we want to get the file list. So how many data files do I need to read through and iterate on? Once we have this file list, we can then programmatically either iteratively loop through this process and get the data file, or use a more vectorized approach to then perform coulomb counting operations. So we're going to load in from our last lecture the coulomb counting function. And if you recall, that takes in our column names. So what we're going to do is first give new column names in the event that we have a charge or a discharge file. We want to make sure that we can do a concatenation. So we're going to keep all the column names consistent. And we do that by setting a new column name using df.columns. And then also what we're going to do is specifically rename our voltage, right? Or get our voltage and current extracted. And once we have that, we're going to use our coulomb counting process. So we pull out what our current is for each instance of time, and then we're going to calculate what that amp hour throughput has been for a given test condition. Ultimately, in this function, we're going to return the throughput that has passed through a battery over time, the average temperature that was observed, and the average current that was observed as well. Now, the next function that we're going to want to bring in is a data frame reader. And so what this will do is essentially, given a file path that we have, we're going to create a CSV data frame using pandas. And we're going to give that the new column names. Again, we want to make sure we've got a consistent column basis. And then given the throughput, temperature, and current, we're then going to return an output of a list of what that throughput and temperature and current were. And so what this is going to do is essentially we're going to say, hey, for each file, run through this process, read the data frame, and then run the coulomb counting function so that I can then get these output values that I'm interested in and feed it into a list. What we can do with that list is then perform some aggregation operations. And so what I'm going to do is specify this path where I have the coulomb counting data. I'm going to create an empty list for our aggregated cell test data, and then I'm going to iterate through the cell IDs. Now, admittedly, using a for loop is not computationally efficient. There are other ways that we can load through the test data. But there are only 7,000 files here, and each file is a couple 100 kilobytes long. So this is pretty manageable, but if we were dealing with, let's say, gigabytes or terabytes of data, or even petabytes, we'd want to go through a more vectorized approach for efficient computation. Now, with that, we're going to run this for loop. And so what we have is essentially a throughput counter. So at the very beginning, we initialize that to 0. We're going to look at the cell test data and give that an empty list. And then for each file, we're going to open that. We're going to read it into a data frame, get the throughput using our previous function, figure out what the total throughput is relative to the test. So if this is the same battery, but the second test, we want to look at how much cumulative energy has passed through the battery. And so we've got a function that is then adding that. And we're taking the absolute value because you have to consider energy is passing either through charge or through discharge. Either way, there has been a transfer of energy between the battery, and that can cause some degradation. We're then also going to do the same process, right? So we're ripping out the temperature, the current, and then what we're going to do is then feed that into a dictionary where we have our throughput, our temperature, current, and our cumulative throughput. And what we're going to do is then append that to our list. So we're going to have a list of dictionaries that we can then easily feed into a pandas data frame so that we can look at the aggregation for each cell and look at how much throughput has passed, what the cumulative throughput is, and then what the average temperature and current is for each of those different test conditions. Now this one is going to take a little bit of time because it's a for loop, and so I'm going to pause the video, but first we need to run the cell where we declared our functions to get that to load, and once that's loaded in, we'll go ahead and run this cell. Okay, so great. So now the aggregation has finished, and just an aside, if you're ever curious and want to figure out how long an operation is going to take, one of the things you can do is load a magic command like %time or %time it, and that can tell you how long the operation is going to last. And so, just an example, if you're curious and want to see in the future how long different operations take for speeding up your computation. So let's go ahead and load the aggregated cell test data list. So again, you'll see each dictionary data set. So we've got the battery ID, that is our key, and then the values is that list of dictionaries where we have our throughput associated with its value, the temperature, the current, and the cumulative throughput. And we've got that for each battery. Now let's go ahead from here. So now that we have this data, where do we go from here? Well, we've ran our coulomb counting, we've aggregated them to a nested dictionary list for easy readability. So now what we're going to do is pass this through a new data frame. We're going to output that to a copy in the CSV format, and we'll go ahead and get to plotting. Now if you're unfamiliar, there's plenty of ways you can output data in the pandas library, such as outputting to a CSV, a JSON, or an Excel-based file. What we're going to do here is we're going to pass that to CSV, just because that's pretty portable and usable. So first what we're going to do is we're going to create a list, and that's going to read in here our output data. And so for each entry in our aggregated cell test data, we're going to look at the key, which would be our battery cell ID, and the values that are associated with it, we're going to extract those out. So we're extracting the throughput, the temperature, and the current that's being passed, and we're going to pass that in. And so what this is going to look like then is essentially a flattened data set that we can pass into our pandas data frame. So we'll go ahead and run that process, and this should be fairly quick, and you'll see it's nearly instantaneous. So now we've got our cell ID. This is a long skinny table where we have multiple iterations of the same cell ID, but we've got each file associated with it. So we've got the throughput as it's changing over time. You'll see that that's negative, right? Because sign notation, you're going to have charge and discharge being on opposite ends of that spectrum. We can see the temperature during the operation too. This is interesting, and we'll load in the metadata along with this, so you can see. But the temperature actually of the chamber is fixed for each battery ID during operation, except for one or two that do mixed temperature or mixed C rates. So what's cool and interesting here is you can see that during the charge profile and the discharge, we're actually getting a significant change in the observed temperature of the battery. Almost it's about 8 degrees Celsius. So that's pretty significant, pretty interesting to find. Not too surprising that part of that would be due to having a much higher current or load being applied to the battery. So if you look, the load during charge is only around 0.7 amps. It's about a fifth to a sixth of the amount that's being applied during discharge scenario for this particular battery. Great, so now that we have this data frame, what we're going to do is get ready for plotting. And what we're going to do to really make this efficient and quick for analysis is use the group by method. So we want to look at the capacity retention of the battery, and we also want to look at the total throughput, so that we can plot our capacity retention versus the throughput that the battery has passed through. And then we might want to layer and look at how that changes for different temperatures that are being applied to the battery or different currents that are being applied. So what we're going to do is we're going to approximate the cell capacity for beginning of life based on the maximum throughput that any single charge scenario can provide. And so we're going to use that, do that using the group by method. So we're going to group by our cell ID, look at the throughput, and take the max value, and we're going to throw that into a dictionary. And so we'll have this dictionary of cell maximum throughputs that's associated with the cell ID and the maximum value. Then we're going to have our capacity retention list and a list of the capacity values. So for each entry in our new data frame, we're going to iterate through and look at the cell ID and then calculate what the capacity is for that one relative to its initial throughput. So if we look at, for example, if it's the maximum capacity and we're dividing it by itself, this is essentially the beginning of life that we would observe. And so we're taking that, and then we'll append it to our dictionary. So we'll then add this to our data frame as a new column, our charge approximate capacity. And then that should give us a new ability to plot our capacity versus time. So this is interesting. Here's our example. We can see, right, if we look at battery ID 30 and battery ID 7, we now see the charge approximate capacity, how it starts at 1 and then tapers down. Now you'll notice it's not the first test initially that hits the maximum capacity. And there could be some reasons for this. Perhaps the test wasn't started truly at the battery's complete discharge, going to a complete charge. Another reason that we could say this is, if you look, the first test is discharge, and you're always going to get less out of your discharge than your charge if you're truly trying to completely, discharge or charge the battery. You can always put in more than you can take out, right? That's the law of entropy. So with that, we've now got our charge approximate capacity. Let's take a sample and just see what we can infer from some of the data sets. So everything is looking good. We've got the throughput, we've got the capacity from it. Now what we're going to do is then add a unique column. So if we want to look at and plot the data effectively, we'll need to know what the temperature is of the battery. what the current was that was applied. And then also we'd want to look at what the conditions were that were applied. So look at the set of how many unique different battery test profiles do we have when we look at the combination of temperatures, the current, and the voltage range that's being applied. So what I'm going to do is first load the data, the metadata, and we're going to merge that using a left merge. And so we're going to take the cell ID, and on each matching cell ID, populate in that information. So we'll go ahead and do that. And then also what we're going to do is then afterwards create that unique ID column. So I'll start with the merge so you can see what that looks like. Okay, so now you'll notice we've got a lot more information. So we've got all our info up through charge, approximate, capacity. Then we also now have loaded in our ambient temperature, the charge profile, discharge profile, our voltage min and max, and then our EIS low and high bounds. Now, if I want to look at a sample, that might be more meaningful so you can see the variation. Now let's just take a sample of 5. So you can look at the difference in the charge and temperatures. So here we see 3 different temperatures. The charge profile, the load doesn't change, but we do see in the discharge it looks like we have different conditions being applied. And the minimum voltage also, it looks like it's changing. We've got some at lower bound of 2 volts and some as high as 2.7 volts. Now, like I said, we're going to create that unique condition column so that we can then have something to filter based off of when we're slicing and dicing our data to truly look at a comparison of all temperatures for the same current applied, same voltage range, right, and for the same battery ID. So we'll go ahead and run that, and you'll notice at the very end, I also have it set up so that we're outputting the data to a CSV format. That's just so that it's quick for recall. So we don't have to go through that time-consuming process of reading through the data again and again. So we're going to go through and run this. Okay, and now let's take a sample of that data. And I'm just rereading it just, as a quick check. And you can see we now have our unique condition column. This is a string entry. It's not supposed to be super reader friendly. It's just supposed to be something that we can pull a set off of and filter. Okay, so now we've got this aggregate data frame. We have our different cell IDs. We've got each entry of how many tests were conducted. And then we have the capacity across the life of the test. So now let's go through and create a simple plotting function using matplotlib. So I'm going to create this function cell plotter. In this, we're going to pass in a data frame. And from that aggregate data frame, we're going to take the list of unique cell IDs. And then for each of the cells in that cell ID, we're effectively going to filter just to that cell. We're going to extract out the cumulative throughput, and that'll be our x-axis, and then the capacity retention is going to be on our y-axis. We'll plot those and then give it a label for each cell, and then we'll go ahead and apply some simple labeling, right, so it's easy to understand. Now, because there are 33 different battery cells, 7,000 files, this is going to look extremely messy if you were to load in all the data. So to start, I'm just going to load in with the data set for where the ambient temperature is 24 degrees. Okay, and so if we look at this, a couple interesting things we should note here to start off. So first, you'll see, look at all these sporadic outliers that are present. So we've got a couple capacity retention values at the very beginning, within the first 50 cycles, that are looking like they're totally killed. 20% capacity, 40% capacity. And we see right after that, between 50 and 200 cycles, capacity near 90%. So this obviously doesn't make sense. We could pass this off. If we had more information about the test being conducted, we'd probably understand that this was a partial charge. Maybe the test got interrupted. But clearly this is something that we can exclude and not consider further because, practically speaking, the capacity of the battery is not magically going to go from a 20% retention value to 90%. Now, outside of that, we do see this interesting trend, right? So you can see it's a slight, almost a linear decay for some of the cells, and for other cells, there's this initial kind of plateau down on a little, concave up curve, followed by a more linear process. And so, if we look at battery ID 36, for example, you can see that linear process, and then on the purple curve for battery ID 34, some of them more kind of just jolted process, but decreased nonetheless in capacity over throughput. Now, a couple things that we might want to consider here. We see clear differences in how quickly these cells or these battery cells are degrading. Well, we know that there are different voltage ranges being applied, some harsher than others, and we also know that temperature can speed up or slow down degradation as well as the load. So, we'll look at that further. One item to note is, we see this resetting capacity every 50 cycles or so. You notice how it looks like there's a slight climb every 50 cycles across each of the data sets. Well, we might be, quick to just dismiss this and say this is measurement error or something similar to what we did with the 20% capacity retention values. But actually, if you look into this and you examine the date times, you'll notice that there's a rest period between testing. And what we consistently observe is that as you apply a period of rest to the batteries, that you can get some additional usable cyclable capacity restored to the battery just by allowing it to have that period of rest. So getting it back to a more steady state condition, and then you'll see this gain in capacity for the next few cycles. So let's go ahead and create a scatter plot matrix to look at this a little bit better. And so to do that, I want to filter some of the measurements of interest. So we're going to create a Boolean mask to look at our unique conditions. And then off of that Boolean mask, we're then going to filter and look at the retention difference. So we want to look at the absolute difference in capacity retention. We're going to filter out rows where we see a capacity retention dropping more than 5%. So hopefully trying to get rid of some of these clear outliers. It's not going to be perfect though. And then we'll reset our data frame. So I'm going to go ahead and run that. Okay, so this shortened up our data frame. We now have 4,200 rows. And then with that subset that's been somewhat cleaned, we're then going to look at our scatter plot matrix. So I'm going to create a subset of our data again, looking at the 2 amp condition. So we just want to filter and look at all batteries that have gone through a discharge profile of 2 amps. We're going to pull out the unique conditions, and for each of those, we're going to make a subplot. So there should be 4 conditions here of different temperature and perhaps a different voltage range being applied. And so we're going to create that temporary data frame, temp_df, using that Boolean masking so that we're just focusing on that specific temperature. Then we're going to look at the unique conditions, and for each unique condition in that temp conditions, we're going to create our new data frame. And so that is, for example, if we have multiple batteries that are being tested under 25 degrees C, we're then iterating through and plotting them all on that same plotted axis. So we're going to go ahead and do that. We'll set the X and Y limbs just to make it more reader friendly. And then we're going to plot the cumulative throughput based as a function of capacity retention. So I'll go ahead and run this plotting function now. Okay, so what you'll see if we look at this on our 4 corners, we can look at and identify that we have, it looks like, a different amount of data being applied to the different test conditions, right? So at 4 degrees Celsius and 20 degrees Celsius, for a 2 amp applied process, we have a lot of duplicates, of cells being tested. However, those cells are being tested under different voltage profiles. And what's interesting here that you can note is how they decay differently. So if you look at, for example, the 20 degrees Celsius data set condition, we see that the 2.5 to 4.2 volt battery seems to degrade at a faster rate than the 2.7 to 4.2 volt condition. Mind you, we already filtered for 2 amps, so these are all having the same discharge profile applied, the same charge profile, and they're having the same temperature. So it's interesting that we're seeing for a shorter voltage range, it seems like it's still degrading faster than the wide 2.2 to 4.2 voltage range condition and the 2.7 to 4.2. Perhaps this is due to a more defective battery, or this is actually a more stable condition for this specific battery. Then if we look at the 24 degrees Celsius condition and the other plots, what you should notice is, so the filtering helped to some extent, but it's not perfect. Obviously, we still have some outliers at beginning of life. We can see, for example, at 4 degrees Celsius, a slew of very low capacity retention red values. Again, these are likely just partial charge tests, so maybe it got split up in half or something like that. But nonetheless, if we look at this, you can see that it looks like the capacity retention, again, we see for a wide range, looking at the 2.0 to 4.2 volts, capacity retention seems to be fairly high for that cell. And then low, or the lowest for that 2.5 to 4.2 voltage region. So some interesting, kind of things to look at there. And then finally, at the other temperature conditions, we don't have additional voltage ranges to look at, so not much to really make there. Now, we could also go through some more analysis in terms of looking at how the capacity retention changes across temperature. So we could plot and hold fixed current, fixed voltage, and look at the specific temperature. We could also, if we want to take it a step further, and look at how capacity and degradation is tied to these unique variables, let's say temperature, current, or amp hour throughput, we could use a correlation, such as the Pearson correlation, and make a heat map to look at that. And finally, another thing that we could look at in the future is doing some machine learning and try to predict the battery's capacity retention as a function of amp hour throughput. That's not the scope for this video. We'll probably tackle that in a future one. But let's kind of summarize what we've done here so far. So in this video, we've looked at the different battery cells in the NASA dataset, all 33 of them. We created a function to perform coulomb counting, and then we iterated through that function for all the batteries in the dataset and for each test condition. We identified and highlighted how it's important to always check to make sure that the headers are consistent when doing a large-scale data operation, such as reading 7,000 CSV files. And then we also highlighted how data cleaning is still required after you've read in those files, right? And that should be evident from these plots here. So with that, we've gone through just a very brief overview of what lifecycle aggregation might look like using Python. I hope you've enjoyed it, and if you have any questions, please reach out, send something in the comments below. That's all for this lecture, and we'll see you next time. Thanks. Bye. Hey, thank you so much for watching this video. I really hope that you found it useful. If you want to look at more videos for battery data analysis or PyBEM and learning about some of its basic features, go ahead and subscribe to this channel. If you have questions, let me know in the comments. I'd love to see what content you would find useful. Thanks so much, and we'll see you soon.